A foundational element of modern cosmology is now under serious examination, following groundbreaking revelations from the James Webb Space Telescope, JWST. The latest images captured by the telescope have astonished scientists and theorists, presenting visual data that not only questions long-held cosmological assumptions, but also signals a potential transformation in our understanding of the universe. These images have sparked intense discussions among astrophysicists, particularly regarding the structure, age, and rate of cosmic expansion. Previously, the Big Bang theory offered a comprehensive model. The universe began about 13.8 billion years ago from a dense singularity and has been expanding ever since. But JWST's findings are revealing a cosmos that is far more complex than previously imagined, possibly shaped by unknown forces or particles yet to be discovered. A long-standing issue in astrophysics known as the Hubble tension lies at the heart of this scientific upheaval. This term refers to the discrepancy between different methods of calculating the universe's expansion rate. There are two principal techniques for estimating the Hubble constant. The first involves examining the early universe through the cosmic microwave background, CMB, the afterglow radiation from the Big Bang. The second measures the current rate of expansion by observing nearby celestial phenomena such as Cepheid variables and Type Ia supernovae, commonly referred to as standard candles. However, these approaches yield conflicting results, with early universe data suggesting a slower expansion rate than what is observed locally. This inconsistency has puzzled cosmologists for years. The CMB, first detected in the 1960s, provides a snapshot of the universe when it was just 380,000 years old. By analyzing slight fluctuations in the temperature and polarization of this ancient radiation, scientists have tried to reconstruct the universe's early expansion. Conversely, local measurements rely on the brightness of stars and supernovae in nearby galaxies to determine their distance and infer the present-day expansion rate. Yet despite advances in technology and observational techniques, the two methods still produce divergent values for the Hubble constant. Hopes that improved precision would eventually align the results have been dimmed by JWST's new data. Rather than resolving the conflict, the telescope's observations have added complexity. Designed to peer deeper into space and further back in time than any previous instrument, JWST has delivered data that aligns with the higher Hubble constant values derived from local measurements. This finding undermines the CMB-based predictions and intensifies the mystery. Nobel laureate Adam Rees, a key figure in this research, has remarked that this agreement with local data suggests the discrepancy isn't due to measurement errors, but indicates a fundamental gap in our theoretical models. The implications are profound. One possibility is that the laws governing the early universe differ from those in effect today. Perhaps dark energy, the enigmatic force accelerating the universe's expansion, isn't constant over time. Others suggest that unknown forms of matter or energy might have influenced the early cosmos, distorting our interpretation of the CMB. Some theorists even propose that the universe may not be as homogeneous and isotropic as previously assumed, and that large-scale irregularities in the distribution of matter could be skewing our measurements. Another critical tool for understanding cosmic structure is gravitational lensing, where massive celestial objects bend the light from background galaxies. This phenomenon allows scientists to map the distribution of dark matter, which doesn't emit or absorb light, but constitutes most of the universe's mass. Yet JWST's lensing data doesn't always align with what the CMB would predict. Observations imply that matter is more unevenly distributed than expected, challenging existing gravitational models and our understanding of dark matter behavior. Both dark matter and dark energy continue to elude direct detection, despite dominating the mass-energy content of the universe. While black holes once seemed like possible explanations for many gravitational mysteries, they now appear to be only part of a much broader, more intricate puzzle. JWST's findings suggest that dark matter might engage in interactions we haven't yet identified, or that dark energy's effects vary over time. This crisis in cosmology is daunting but also exhilarating. It signifies that the universe still holds secrets we are only beginning to uncover. Despite the challenges, the scientific community remains hopeful. Historically, major breakthroughs have followed periods of intense theoretical conflict. From the realization that the universe is expanding to the discovery that galaxies rotate too fast for visible matter alone to account for their motion, each contradiction has led to deeper insights. Today's cosmological tension, sparked by JWST's revolutionary observations, may herald the next scientific paradigm shift. It compels a re-evaluation of long-held beliefs and may pave the way for entirely new physics, redefining our understanding of time, space, and existence itself. Scientific progress thrives on challenges. Theories are not immutable truths. They are tools refined and updated as evidence demands. With JWST continuing to transmit data from the farthest reaches of the universe, we are witnessing a transformation in real time. It is a humbling reminder that the cosmos is more ancient, vast, and mysterious than we ever imagined. Although we may not have definitive answers, we are now better equipped to ask the right questions, each photon bringing us a step closer to understanding the truth. This moment represents a turning point in astrophysics. The gap between early universe predictions and current observations isn't a minor flaw to be patched. It suggests that our foundational models may be incomplete. JWST has revealed galaxies that are more massive, more luminous, and more developed than they should be given their distance and age. If these galaxies formed so early, it challenges the Big Bang model's assumption that structure formation takes significant time. This could imply a flaw in our timeline or a fundamental misunderstanding of how galaxies form. For decades, cosmology has operated under the assumption that the universe expanded uniformly from a single origin point. But JWST's observations indicate that ancient galaxies appear as mature as ones nearby, implying that cosmic evolution might not be as linear as previously believed. Some researchers even speculate that our understanding of time might be incomplete. Could time have behaved differently in the early universe? Might redshift, traditionally viewed as evidence of expansion, also involve unknown quantum or relativistic effects? In response to these tensions, alternative cosmological models are gaining renewed interest. One such theory is the cyclic universe, where the cosmos undergoes repeated cycles of expansion and contraction. Another is the emergent universe model, suggesting the universe existed in a steady state before beginning its expansion, eliminating the need for a singular origin. These models may help address some of the inconsistencies exposed by JWST. Beyond expansion rates, JWST data is also questioning the very structure of space. Gravitational lensing reveals that matter isn't as uniformly distributed as the CMB suggests. This discrepancy supports the idea that unknown forces or interactions, perhaps involving dark matter or dark energy, played a significant role in shaping the early universe. The CMB shows a remarkably uniform young universe, but the present-day cosmos is filled with clumps and clusters. Traditional models propose that dark matter provided a framework for visible matter to gather, but this alone doesn't fully explain the rapid formation of galaxies. Scientists are exploring more speculative explanations, including possible interactions between dark matter and dark energy or even undiscovered forces. Adding to the complexity, JWST captures light from galaxies billions of years old, allowing us to see into the universe's distant past. Yet these early galaxies appear unexpectedly developed, suggesting that structure formation happened faster and under different conditions than current models predict. Some theorists propose that these galaxies could be remnants from a previous universe, their structure imprinted on ours during a cosmic rebirth. Others believe they may be evidence of entirely new physics. These questions have implications far beyond astronomy. If physical constants like the speed of light or gravitational strength varied over time, it would suggest that our laws of physics are not fixed, but evolved along with the universe. This idea, once considered speculative, is now being taken seriously due to JWST's findings. Even dark energy, often treated as a placeholder for our ignorance, may be something more complex. It could be a dynamic field, like the Higgs field, changing over time and space. influencing how galaxies form and move. Some theories connect it to quantum vacuum fluctuations or the structure of spacetime itself. The old notion of a constant, dark energy may be due for retirement. Moreover, quantum effects on cosmic scales are becoming an area of serious study. Normally confined to the atomic realm, quantum mechanics may have influenced the universe's large-scale structure during the inflationary period just after the Big Bang. Fluctuations from that era may have been amplified by exotic physics, traces of which JWST could now be detecting. In short, the universe is revealing itself to be far more dynamic, ancient, and mysterious than our current models can explain.